Welcome, everyone. Nice to see you all again. I'm glad to welcome today Oren Hollander, the CEO of Hands-On Training. Oren is a senior lecturer whose expertise lies in ARM, security for embedded systems, and FPGA. Today, Oren will be presenting securing your microcontroller with ARM TrustZone Technology. Now, just a little housekeeping before we get started. As usual, the presentation will take around an hour, followed by a 10-minute Q&A. I invite you to share your questions in the chat box, and we will answer them after the presentation is over. And as usually, we will also record the session, and we will upload it later on our YouTube channel. Oren, I would like to invite you now to start your presentation.
Thank you very much, Andrea. Okay, do you see my screen?
Yes, it's perfect.
Okay, so welcome everybody. Thank you for joining this session. We are going to talk today about how to secure your microcontroller with ARM TrustZone technology. To give you a quick review what we are doing. So Hands-On Training is officially ARM training center. So we train all of the silicon vendors around the world, companies like Apple, Samsung, Broadcom, Marvell, NVIDIA. These are our customers. Plus, of course, customers that use off-the-shelf ARM processors. It could be in FPGA or in ST or in XP or TI or whatever. We also Intel FPGA training center around the world, Microsemi, which is Microchip today, and NewAE, which is a security company that develop the Chip Whisperer and other products that hack different hardware in order to, with side channel analysis and fault injection. So we are their training center as well, and we train these courses all over the world. You can find more information in our website. Okay, so our agenda for today, it's condensed, so we have a lot of things to talk about. So we will start with, as you can see here, embedded software vulnerabilities and common attacks. I'm going to do that shortly. Then we are going to describe what is TrustZone technology for ARMv8-M, because usually most of the people are aware of TrustZone for Cortex-A. Then we will go deep dive into the architecture features in order to see how the TrustZone was actually implemented on Cortex-M and how it helps you to secure your microcontroller or your complete solution. Then we of course are going to cover the toolchain support to see what kind of things are supported by the compiler and other stuff. And last but not least, we will of course discuss, is TrustZone security enough, or should the silicon vendor or you do something else in order to make your solution secured from edge to edge. And at the end, we will have, of course, a question and answer session to see what's going on. Feel free, as Andrea mentioned before, feel free to type in the chat box any question that you have, and I will try to address all of them. If we'll not have too much time, enough time, I can address this at the end, maybe after the session as well. So you have my email on the first slide, so you can contact me for questions if needed. Okay, let's start. So before I, let's say, designed or generated this presentation, I thought a lot how to put this complex topic into 1 hour and make it interesting and not boring. So I will start first of all with a quick description about the embedded software vulnerabilities and common attacks we have today, and then we can go specifically to the details. So as you know, we have come a long way from the time when embedded systems were meant to run a single application where today embedded system behave like mini computers. So smartphone market is an obvious example for that. With ever-growing demand for enhanced capabilities and new features, increased digitization and turning dumb embedded devices into smart ones via AI, interconnectivity, so does the complexity of embedded systems and operating system is increasing as well. And as you know, as software, of course, is becoming more and more complex. It also means more bugs. Some of these may be security bugs, some of them programming bugs. Like computers, many embedded systems have security vulnerabilities, which include software errors that can provide for an attacker to gain access to the system. The result, as you will see in a second, of such vulnerabilities could lead to serious security implications. For example, if security bugs exist in the Linux kernel, the entire system could be potentially compromised. Yeah, in this session, we're going to talk about microcontrollers, not about Linux, but it's just an example. Unfortunately, the increase in size and complexity means that it is not possible to examine all the OS software for security vulnerabilities and issues. So an attackers or an attacks can easily work their way into devices through vulnerabilities, to operating system, and we need, of course, to find solution for that. We know also that embedded software security should manage and respond to malicious behavior happening in the embedded system, both during the initialization process and in real time. So we would like to provide, let's say that secure software should provide application protection isolation. We should ensure the integrity and authenticity of application that we run on that device. We should ensure the confidentiality of our data. That means we need to protect our data at rest. And that, of course, include as well the user data. We need to protect from network attacks. And of course, we also need to protect the data. One, is it in transit from point to point? Let's see, but before we begin solving the problems of software security in embedded systems, we first need to understand what are the potential vulnerabilities that are related to embedded system software. What are the attack vectors that are used against embedded system software? And of course, what is the impact of such attacks on assets we wish to protect? Now, to be honest with you, there's tons of attacks every day and every year. And I just want to give you some nice examples that I found they are useful in order to understand how much, let's say, efficient could be an attack on microcontrollers. So I decided to use 3 examples from real use case from the world. The one that probably, which is the most probably familiar with you, is the famous malware given the name Stuxnet. So anyone who knows Stuxnet, which is believed to be the world's first true cyber weapon, is an example of an advanced persistent threat attack, what we call APT, very sophisticated one. It also the world's first attack that target demonstrates the incredible sophistication potential in modern embedded security attacks. So the Stuxnet malware, which was discovered in 2010, infiltrated the Siemens process control system at nuclear plants in Iran. It destroyed over 2,000 uranium processing centrifuges. And Stuxnet used several zero-day attacks to subvert the security of Microsoft Windows workstation of the nuclear site operators. From there, it sought out Siemens Step 7 software, which is also Windows-based system, used to program the centrifuges. Finally, it's, as you can see here, it's compromised the PLC, the program logic controllers, were directly connected to the centrifuge motors. Why I'm showing that? Because Stuxnet demonstrated the need for improved security skills within the embedded development community, and also contributed to the understanding that higher level of assurance in critical infrastructure is required than with standard commercial IT practices. Okay? So this is one software vulnerability. Second one that I would like you to be aware of, called the LoJack attack, something that I really like. LoJack is a firmware attack that can survive even if the operating system is being reinstalled of the hard disk or embedded store, or even if you replace the embedded storage. The LoJack, which was discovered not too many years ago, by the way, in 2018, and it is believed to be developed by the FancyBear. If you're not familiar with the FancyBear is a Russian cyber group specialized in cyber attacks that are classified as advanced persistent threats. The idea behind this attack is that LoJack takes advantage of vulnerability in what we call CompuTrace LoJack. It's a piece of software that comes pre-installed on many computers, UEFI. UEFI is the successor of BIOS, if you are not aware of, and this is the key to any computer. Since both are firmware stored in a separate memory found on the motherboard, and both contain the instructions that control the operation on the computer circuits, all of which means that it doesn't rely on operating system. So that means UEFI, of course, is used today in many modern embedded systems, probably on every PC that you are using. So once the malicious attachment is executed, either by the user or by the attacker himself, the malicious payload uses a vulnerability that they found in the CompuTrace LoJack to talk directly to the SPI controller in the chipset, which controls access to the SPI chip, which contain the UEFI firmware, to apply malicious patch to the UEFI firmware. After that, after this patch is of course applied, then it runs every time during the boot process and patch the registry of the Windows operating system before Windows starts to ensure that its services run on every boot, even if the system was wiped and re-imaged. So it's nice. It's permanent attack. Okay, then anyone can do whatever he likes with that. He can read and write files, collect data on the system, launch exploit, do everything remotely. So as we will see, as secure boot, for example, could prevent LoJack attack. But there was vulnerability. And last but not least, because again, there's a tons of attacks, I just want to show the sexy one, if you call high-tech sexy. But as you can see here, we have the clock screw attack. So this is one of the most famous software attacks on CPU in the field. The idea here is that this attack exploits the dynamic voltage and frequency scaling, or if you like, DVFS, to break confidentiality and integrity on modern processors such as ARM CPU, but not just ARM. DVFS, if you're not familiar with, is a technique used by CPU vendors to save energy by regulating the frequency and the voltage of the processor cores according to the runtime computing demands. So, for example, if you run a game on your smartphone, then the system will increase the power and frequency, voltage and frequency. However, if you just read email or you're going into, or you're doing some housekeeping things, then it will decrease dynamically the voltage and frequency in order to save battery life. So for DVFS to work effectively, hardware and software need to cooperate together and with a very fine granularity. The clock screw attack, exploits software access to energy management hardware to push the operating limits of processor to the point of inducting faulty computation. The idea is to take the system out of spec and by that make the system to start generating faults and then start to leak information from the secure world to the normal world. So this can be exploited by an attacker to extract cryptography keys stored in the ARM TrustZone secure area, which is a confidentiality attack, of course, or to load self-signed code to the TrustZone area and violate the integrity check. And finally, an attacker can also cause the system to crash, those performing what we call an availability attack or denial of service attack. So the danger aspect of this attack is that it can be implemented remotely without physical access to the hardware by tricking the user to download malicious code. Okay, so these are just 3 important examples about why embedded systems are vulnerable. Now let's put these attacks aside and let's start our webinar, okay, by going into the TrustZone technology for ARM v8M. Okay. So, first of all, today ARM TrustZone technology, if you're not familiar with that, is the foundation for security in application processor, protecting billions of devices each year. Examples of areas where TrustZone has been used include authentication. So some smartphones come with iris scanning as well as fingerprint sensor to replace passwords, as you know. Mobile payment, very famous thing today, is protected by TrustZone-based Trusted Execution Environment, or TEE. Content protection, over the top, what we call OTT, is the modern way to consume content on your smart DTV or mobile gadget. This relies again on TrustZone media protection, and it has been protecting HD stream content since 2011. And of course, enterprise security. So Samsung, for example, has pioneered enterprise security with TrustZone, providing the hardware isolation technology necessary for integrity, management, and introducing the concept of trusted application. ARM TrustZone for application processor is a mature and successful security architecture foundation, requiring the silicon provider to integrate it and the OEM to use it. This is particularly true as TrustZone extends beyond the processor to include the concept of secure peripherals, secure memory, and secure interrupt. So if someone thinks that TrustZone is just for the CPU, it's not true, because TrustZone is a brand name which contains behind it a lot of IPs, and many of them are used by silicon vendors in order to provide, let's say, coast-to-coast security on the SOC or edge-to-edge. Okay, the idea behind it is that the future, as you know, of the Internet of Things, that will be everywhere, in your connected car, the doorbell, the door lock on your house, connected AI and monitoring and a lot of stuff. The threat model for different devices will vary. For example, an engineer developing a door lock for a smart home would need to consider the authenticity and capability of its associated application, as well as the possibility of physical tampering, whereas a smart sensor might have a smaller set of requirements around authentication and identity. So different products, different threat models. It is clear, I believe, that nearly all such applications will require a robust security foundation. So before the announcement of the ARM v8M architecture, I will talk about it in a second, the security solutions available for microcontrollers were limited. This meant that engineers had to design their own crypto subsystems. The original TrustZone security solution does a great job for Cortex-A profile, but it's expensive and not architecturally compatible with the ARM microcontroller system, or the Cortex-M. Okay, so in November 2015, 6 years ago, ARM v8M was launched. Okay, one of the main differences between these and the previous version of the microcontroller profile of the ARM architecture is the new ARM v8 security extension. This is what we are going to talk about today. Are there any questions up to here? You can type them. If not, let's go deep. Okay, so now we are going to see what kind of things were added to the architecture and how it actually helps us to develop more secure solutions. Okay. First of all, before I'm going into the slide itself, just to make everybody aligned, in the last few minutes I mentioned ARM v8 architecture. So people who are not familiar with ARM, it's maybe mandatory to mention that ARM doesn't develop silicon; they develop IP, and then the silicon vendor take a license, let's say, the architecture or specific off-the-shelf processor that is based on that architecture. For example, Cortex-M4, M7, M33, etc. And each processor that ARM provides is based, of course, on specific architecture. The ARM v8M is the first one with the TrustZone security extension. There are other things that were added, a lot of new instruction and other improvements. However, the security extension is the most, let's say, big change here. The current Cortex-M devices that are part of the ARM v8, and by that they have the security extension, are Cortex-M 23, 33, 35P, 55. Okay, currently. So we have currently 4 kind of microcontrollers families with security embedded inside. Now, to be honest, the security extension is an optional one. That means you can find in the market Cortex-M devices like Cortex-M 33, for example, without security and with security. One example for that is, for example, the NXP device LPC 55S69, which has 2 Cortex-M 33 in the package, one with security and one without a security extension. Okay? So this first thing to mention so everybody will be aligned. What we are going to talk here is, of course, about devices that implemented the security extension. So the ARM v8M security extension is ARM's solution to provide confidentiality, integrity, and authenticity within the microcontroller world. Okay? The new extension is conceptually similar to ARM existing TrustZone solution found in Cortex-A. However, as I mentioned before, it has been optimized for microcontrollers. For example, the TrustZone security solution found in Cortex-A provides 2 states, secure and non-secure, which both have their own 4 GB address, or maybe more, depends on which Cortex-A do you use, 32-bit architecture, 64-bit architecture. In ARM v8M, the security extension also provides the same secure and non-secure states. However, only 1 4 GB address space is available, which may be partitioned into secure and non-secure regions, as we will see in a few minutes. Secure software running from a secure memory region has access to more system resources, and that means it has more privilege. And non-secure software is restricted to only access non-secure memory. This is guaranteed by the architecture. For example, if a non-secure code attempts to read or write to a secure memory, then the processor will generate a secure fault, which is a new exception that were added, as we'll see later. So to protect secure software, the security extension provides several things. First of all, isolation. It isolates the secure memory for code and data, and it provides secure execution state to run secure code. So isolate non-secure code and secure code. The latest compilers provide support for ARM v8M, allowing users to build both highly trusted secure software as well as non-secure applications. So both secure and non-secure software may call each other through a common API, as we will see later. So what you can see here, you see the application code. So as you know, Cortex-M has two modes for the microcontroller, the thread mode and the handler mode. Thread mode run applications, and handler mode, of course, run exceptions like interrupts, abort, and things like that. Once we add, of course, the security, then there's a partition, as you can see, for secure and non-secure regions on the same piece of hardware. That means the same microcontroller. So that's the main idea here. Now, of course, in case we build such an architecture, we need a way to call between different secure states. So non-secure code may ask for services from a secure area. For example, I would like you to encrypt a buffer for me, or I would like you to purchase a book for me in Amazon or whatever. Of course, the secure code may also need to call the non-secure code for something, okay, to provide him some information or run several tasks or call a peripheral or whatever. So there's of course, secure code can call non-secure functions in this architecture. Non-secure functions and data should not be trusted, of course. Non-secure code can also call into secure libraries, but only subset of secure code is callable. This is something that is very important in this architecture, and I'm going to expand or elaborate on that in a few slides. So secure entry points are limited. The idea is to make the hacker life very hard, not provide too many doors between the non-secure world to the secure world. So the architecture actually provide only two options from going from the non-secure to the secure. One of them we'll see called the secure gateway instruction in a specific region in the memory, and the other is through a secure interrupt, okay, that we will see also. Of course, non-secure code doesn't need to know it is calling a secure function, as we will see. This is, by the way, is different from ARM v8a TrustZone, where changing security state can only occur on an exception boundary. Here, there are two ways to do that. Okay, so let's start with what needs to be done or what has been done with this architecture. First of all, let's talk about memory security and rules. In order to enforce security, we need to do two things. First of all, to design or isolate things in the architecture. Second, enforce it on the bus signals to make sure that it will not be enough for a hacker to manipulate some software bits in order to go to a, let's say, to a prohibited, let's say, area. So physical memory, as I mentioned before, is split into secure and non-secure regions. A secure region can also be what we call, this is something new, non-secure callable, or NSC, okay? This is like a gateway. That means in order to go from the non-secure to the secure, you cannot just manipulate a pointer and jump and make your code jumping to any secure address, even if you know the address. You must go through a specific process, to a specific instruction that I'm going to show later, called a secure gate, and then it will allows you, again, according to some rules, to branch to the secure area. Okay. However, the secure area, the secure code can return back directly to the non-secure code. It doesn't have to go through the non-secure callable region, which is a special region that I'm going to talk about it in a minute. We can return directly to here. So the rules enforced within the processor, it means that the non-secure state cannot access secure memory. secure code cannot be executed from non-secure memory, and secure code can access non-secure data. That means secure code can do whatever he likes, non-secure is very restricted. On top of that, the rules are enforced by also the memory system. So here you can see the AMBA, on the AMBA 5 HB, which we call HB5, it's a new, let's say it's a new revolution or progress of the HB standard. It adds another signal called non-sec. It's a bit that helps to protect memory from other masters. So you can actually, as you can see, you can limit DMA, for example, to just copy things from the non-secure, not just from the secure. That means that even someone maybe cannot hack the CPU and he will try to do some DMA attack, the silicon vendors can prohibit that. Okay, he can prohibit that because he now has another bit on the bus that can be used in order to prevent access to specific areas. Let's continue. So we've seen the rules that apply to the memory security, but the question, the $1 million question here is, how can we determine whether memory is marked as non-secure, secure, or non-secure callable? So what is important to understand, again, without going in too many details, because it's a completely training by itself, the security state of memory region is controlled by a combination of two attribution units. One is called the security attribution unit, what you can see on the slide, SAU, this block. And the second one is an implementation defined attribution unit, which is external to the CPU. It's called IDAU. Both the SAU and the IDAU together are independently optional, but at least one of them is required. Otherwise, there is no memory security. So silicon vendor can use both of them or one of them, but he must use at least one of them. Otherwise, there's no security. So the SAU is available when the security extension is implemented and is found internally within the ARMv8 processor. Okay, so as you can see, the IDAU is external and it's comprised from a kind of an interface and a responder. So the idea that the interface receives the requested address from the processor and send it to the responder. The responder then determines the security state of the address and then returns this back to the interface. So the SAU and the IDAU combine to ensure that when the processor is in a non-secure state, it doesn't access secure memory. The way this works is that when the processor requests an address from the memory, the SAU and IDAU determines whether the address is marked as non-secure, secure, or secure non-secure callable, NCS. And if the address being accessed is marked as secure or secure non-callable by either the SAU or the IDAU, and the processor is currently in the non-secure state, a fault will be raised. So it's like a police officer that's sitting, and every address that the CPU generates for instructional data passes through this filter of police officer, and as long as there's no, let's say, security violation, everything flow without a problem. However, if there's a problem, there's going to be an exception, which will not give you a way to run the software. By the way, SAU it's like the memory protection unit, but it comes before it, and it has also some regions that you can actually program or configure if you like. And I will show you later where you do that in the tools. Okay. Okay. After we finish with the security check, then we also have the memory protection unit, which is very famous on many Cortex-M devices. Here, if security extension is implemented, you actually have two physical MPUs, secure MPUs and non-secure MPUs. The MPU, of course, is a way to partition memory into multiple regions that are marked with different memory attributes. So you can define the access permission for privilege and non-privilege. You can decide if code can be executed there or provide or mark it as execute never and things like that. And by that, you can build a robust software and isolating, for example, your autos from the application or the application for the application themselves. So it's a kind of sandboxing. Now, each MPU could be configured, of course, independently and differently from each other. So in the secure world, you can have specific configuration and treat the let's say the address map differently than in the non-secure world. So you can apply different configuration in each mode. So that's interesting. Now, what you can see here, just a diagram that I wanted to show you, that when here we can see what's happened with the secure view of the system, of the system control space, which is responsible in ARM in specific addresses. It provides all the all the memory mapped registers that could be configured for, as you can see, MPU, system timer, and the nested vector interrupt, the NVIC, and other stuff here, debug features, whatever. So the secure world can see both its own security registers plus an alias of the non-secure registers. Or in other words, the secure world or the secure code that run in the secure world can actually configure the whole device. However, once you are in the non-secure mode, you see just a subset of the complete memory address map. So in that case, you see the non-secure code cannot even see these addresses. Now, if someone asks himself, if someone try to just run a loop and try to access every line in memory, they're going to be, of course, once the code will try to access the secure area, you will get, of course, a fault or exception. How those things actually work? Let's connect the puzzle pieces together. So what you can see here is two examples of boot up configuration. Okay, not runtime. The next slide will show the runtime configuration, but how to start from reset. Okay, so this is just, of course, an example of a boot security map. The all NS or non-secure bit in the SAU control register determines whether memory is marked as secure or non-secure. When the SAU is disabled, it's important to understand that when you reset the system, at the beginning, the SAU is disabled. So your boot code should enable it. But the question, what's happened before you enable it? So there's an option to decide what kind of area in memory will be secure from reset and which will not be secure. So in that case, you can see that there's only one bit. Either you can make it all the regions secure or non-secure, just one bit, 0 or 1. On the other hand, if the silicon vendor provides also the IDAU, then you can define how the system will boot up. So if the SAU doesn't enforce any security, that means it doesn't configure any region. So all of the memory start without any secure. That means non-secure, and the IDAU splits the same address memory into secure, non-secure. Here it's symmetric, but it can be done differently, of course. Then the combination between them define how the system will act in boot time. So in the left-hand side, you see that the result is secure, because secure is higher priority or non-secure. So once you combine them, if you combine secure and non-secure, you get secure. So here you can see that I can have this combination at boot up or this combination at boot up. Depends on whatever you would like to achieve. However, in runtime, you can change the behavior. That means the SAU can be used to reconfigure the combined security settings after boot. So in this example, you see that the SAU configures some of the regions as secure, some of them as secure, non-secureable callable. This will be the area for the non-secure to contact or ask for services from the secure world, as we will see in a minute. And the IDU can be configured completely differently, and the combination between them define what happened in runtime. So this could be changed according to specific use cases. Although most customers configure that from at the beginning and don't touch it, it is possible to fine-tune the settings in runtime. Okay. By the way, you don't need, if someone asks himself if he need to configure, take the whole memory map and configure it completely, the answer is no. Only memory that are not covered by enabled MPU region are secured. That means you actually need to program anything that you would like it to be non-secure, okay, a non-secure callable. All others will be automatically be considered as a secured area. Okay. Yeah. Usually, by the way, in devices you will find up to 8 regions that you can configure, that you can split the area to 8 regions. Although the architecture permits up to 256 regions, usually the microcontrollers off the shelf that ARM released so far supports up to 8 regions. Okay? Some of them 4, but most of them 8. Now let's see how things happened with this architecture. So what you can see, I would like to demonstrate what's happening when you would like to branch between secure and non-secure state from reset, okay, to understand how all of these things actually work. So in ARM v8m architecture, you can switch security state via an exception, just like in TrustZone for Cortex-A profile, but you can also switch security state via function call. Okay, so the diagram that you're going to see now show an example, just one example, of how secure code can call into non-secure code and vice versa in 4 stages. So let's start. Stage number 1. Okay, so first the system may, of course, boot up in secure state and runs secure firmware. Typically, of course, the secure firmware, as you know, carries out some security checks before performing various initialization tasks, such as running C library, startup code, and SAU programming. Second, okay, once the secure firmware has initialized the system appropriately, it branches to the entry point of the non-secure application. The non-secure software typically has its own reset sequence, which includes C startup code and hardware initialization routines, for example, to configure peripherals. This doesn't conflict, by the way, with initialization from the secure code, as the stack and heap spaces of secure and non-secure code are separated. The non-secure software may also include a real-time or embedded operating system. Thirdly, the non-secure application could call secure software via secure API. And finally, secure API might need to call a non-secure callback function, for example, to access a non-secure peripheral. So there's also a way to do that. Now, the specific instruction and flow, how to do all of this stuff, is of course beyond of the scope of this webinar, and it's a 1 day of training by itself, just this process, including all the secure boot and everything. But just to show you. Now, last but not least, what about exceptions? What about interrupts? If we talked about security, security is all about isolation. So we would like not just to split or isolate secure memory from non-secure memory, but what happened with interrupts and exceptions. So interrupts can be programmed as secure or non-secure interrupts. That means the NVIC supports that. Some system exceptions, by the way, are banked. For example, SysTick, there's a SysTick for secure world and SysTick for the non-secure world. There's a new secure fault exception. There's, for example, so there's a lot of things that actually duplicated, not all of them because of the area, but some of the features were duplicated. And also priority of secure exception or interrupt can share same levels as non-secure or can be higher priority. That means you can make all the security or some of them with higher priority than non-secure, or sometimes make a secure interrupt with lower priority than non-secure interrupt. Just to give you an idea, let's take the smartphone. If you now buy something with your phone, for example, a book in Amazon, and during the time that you fill in your details and credit card and whatever, you get a phone call from your mom. Can you answer the call today? Yes, you can. Although the call from your mom or whatever is coming from the non-secure world, it doesn't stop you, even if you're in secure world, putting inside your credit card details. So we call this architecture non-blocking. We would like security, but we also would like a good user experience. So you can define what is the priority of secure and non-secure interrupts. Also, non-maskable interrupt, the NMI, can be configured to target either security state with a specific bit. Same thing with bus fault, if you're aware of that, and other stuff. So what you see in this diagram here on this slide is what happened when you're taking an exception, okay? So the processor, by the way, only secure code can, of course, configure what is secure interrupt and what is not secure interrupt. Yeah, non-secure code cannot configure that. So what happened here if we take an exception is that the processor automatically transitions to the security state targeted at an exception. Secure exception handlers do not need to start with a special instruction that we'll see later, SG, the secure gate. This is let's say when you try to call the secure world with a function call. But once you have a secure interrupt, you don't need this specific branch. You immediately jump to the secure world. An exception vector must be, of course, in the correct memory type. Otherwise, a secure fault is raised. So that means the vector for a secure exception must be in a secure memory. And then, as you can see here, all registers automatically, this is done by the microarchitecture, automatically pushed to the secure stack and zeroed. Why zeroed? Because once you go from secure to non-secure, you don't want anything to leak out. So maybe I didn't say that, but most of the general purpose registers of the CPU are not banked. That means you have just one copy. So when there is a context switch between the secure world and the non-secure world, there's some housekeeping that need to be done. So all the register pushed to the secure stack and zeroed. And then the non-secure world doesn't even know what's happened before. Once the exception finished, then the registers are popped up again. Okay. Stack frame, by the way, can be extended also to hold floating point registers. And of course, and so the bottom diagram here actually shows what's happened when we chain several exceptions. So you see, I'm in the secure mode. I'm getting an interrupt. Okay, I'm still in the secure world running the handler. And when I finish that, I'm receiving another exception, but now from the non-secure world. Okay, so the latency of the first exception here is not affected. Stack frame is just extended when the second exception taken. So it's approximately the same latency as saving basic stack frame. And all stacking and unstacking is done by hardware, which is, of course, happening in all Cortex-M devices. So these are the major important thing regarding the ARMv8-M architecture. Of course, I cannot cover everything in this webinar, but I would like to show other stuff as well. So let's talk a little bit about toolchain support. First of all, okay, I believe that most of the people are aware what is SIMSYS, okay? But to those who are not familiar with, SIMSYS stands for the Cortex Microcontroller Software Interface Standard, which consists of number of components such as the SIMSYS core and the SIMSYS system view description, which we call SIMSYS SVD, sorry, that make it easier for silicon vendors and tool vendors and software developers to design, support and work with different Cortex-M devices. That means that if today you're working with ST Microelectronics Cortex-M and tomorrow you're moving to a new project with NXP or Infineon or whatever, the same API names would be used. So SIMSYS core actually standardized the way that you actually touch the iron or the low level in the CPUs, how you configure interrupts, etc. So of course, because we added the security extension, it must be, of course, supported by the tools. So the SIMSYS core provides template files for startup code and system initialization known as SIMSYS core, with, of course, header files that supporting key processor functionalities such as the NVIC, the MPU, etc. Now the SIMSYS core has been extended to provide a new partition, call it, as you can see, device.age, _device.age, that can be used to configure the SAU region, the security attribution unit. So this file contains a function called TrustZone SAU setup, which you can use to set up. However, some tools such as Kyle MDK, which is coming from ARM, provide configuration wizards in a GUI that make it even simpler to configure the SAU. So you see, you just enable the specific region, you define the start and end address of each region, and by that you can define if it's a secure or non-secure, secure, non-secure, callable, or non-secure. You don't need to define if something is secure, because you see when SAU is disabled or when you configure several regions, all the other regions are automatically secure. So you just need to configure only the non-secure and the secure non-callable area. Second, which is something that it's important to understand, is the ARM C language extensions, or the ACLE. This is a specific source language extension and implementation choices that C compilers can implement in order to allow programmers to better exploit the ARM architecture. So usually the extension include the predefined macros that provide information about the functionality of the target architecture. For example, whether it has hardware floating point or not, intrinsic functions, of course, and attributes that can be applied to functions, data, and other entities. So a new list of requirements for development tools have been created in order to support the ARMv8-M security extension, also sometimes called today, as I mentioned in the slide, CMSE, the Cortex-M security extension, and it falls under ACLE. So, so to work with the CMSE, development tools must meet, of course, certain requirements. These requirements, by the way, are listed in the document, ARMv8 security extension requirement on development tools. This is a PDF that you can download from the internet if it's interests you. However, it's usually for the developers, the tool developers themselves. You are the end users, could read it just to make sure that you understand what actually were added. It supports all the new instruction, the secure software, and import libraries that allow non-secure to secure software calls. So compiler toolchains like ARM Compiler 6 and GCC are CMSC compliant. Okay, of course, the ARM CMSC.h header must be included before using CMSC support. We also recommend that the compilers provide a suitable command line option to work with CMSC. For example, the MCMSC. Okay, so this is something. So all of this new instruction, by the way, secure gateway, BXNS, BLXNS, and TT, which stands for test target, these are specific instructions that were added to the architecture in order to support the extension and how secure code will call non-secure code and vice versa. So to give you an example, if we take a look, CMSC compliant compiler toolchain must be capable of generating a secure gateway veneer. So for each secure entry function with external, for each secure entry function with external linkage. So it consists of an SG, as you can see here, instruction, secure gate instruction. So as I mentioned, you cannot jump directly from the non-secure to the secure. You first need a veneer table where for each entry for each secure function, you have an entry point that starts first of all with the SG. You cannot jump to the branch immediately. You first need to go to this specific instruction. So the SG instruction must be placed into non-secure callable memory. It cannot be inserted here. So the secure gateway veneers decouple the addresses of secure gateways from the rest of the secure code. The idea here is that by maintaining a vector of secure gateway veneers at a forever fixed address, the rest of the secure code can be updated independently of the secure code, and you can update each one of them independently. So therefore, the non-secure code only needs to know the address of the non-secure call veneers, and secure image can be changed if the veneer address stay constant. Okay, again, secure entry functions in the secure memory region can return directly to the non-secure code with a special command called BXNS, branch with exchange to non-secure. Sorry, wait a second. Okay, so note, by the way, that the SG instruction will be treated as a NOP, no operation, if fetched from non-secure memory. So there's no way to trick the processor to switch to secure state when the instructions are being fetched from non-secure memory. It must be located in the non-secure callable region, which is a secure area. Okay, last but not least, before the question and answers, is TrustZone security enough? Okay, TrustZone, the idea is to isolate and protect. So this is a big question, and we don't have the scope here to answer it fully, but to give you the idea, because I work with these things every day. So summary of attack and defense. Here, what you can see here is a list of the greatest and latest attack categories on embedded systems, hardware attacks and software attacks. You see the cost, the goal, the differences, and but what I would like to focus here is the implementation. You see that I highlight here the ARM v8m, what this security extension can handle. So if someone thinks that TrustZone can save his ass, let's say it like that, it's not the case. It's TrustZone can protect most of them, can protect software against software attacks. Again, as long as there's no vulnerability in your secure code, of course. So protecting against Trojan horses, stack attack, or things like that. TrustZone, also privilege escalation attack, that could be a good let's say target for TrustZone. Same thing from probing attack, because we have here the AMBA 5 hardware bit. And of course, secure task info leakage, it's also supported. However, all the hardware attack, as I mentioned at the beginning of this, that we provide training about hardware attacks. So glitching attacks and differential power analysis, what we call side channel attack. These are not protected with TrustZone. TrustZone can be, let's see, can be worked together with hardware blocks in the architecture to mitigate those attacks as well. But that requires to make the silicon more robust and to embed inside some countermeasures. And this ARM provides with the crypto cell and secure core solutions that they have. So it's not in the scope of the TrustZone. TrustZone can only provide security to software that run on the processor, or if you use an extra TrustZone IPs that are external to the processor, you can also protect against other masters like PCI Express attack, USB attacks, DMA attacks, and things like that. To give you several examples, I would like to finish that trusted execution environment, which is where the secure code is running, are not a bulletproof. If you have a software bug in your secure code, that could be make the whole system vulnerable. And I provide here several things that you can Google later and find all of them, by the way, on YouTube. So you can Google them immediately and find the complete demonstration lecture. The first one is attack on TrustZone M, privilege escalation on the NXP device. This is not a software vulnerability. This was used glitching, voltage glitching, in order to bypass some software checks and then get a privilege level in the secure world, so you can do whatever you like. In Black Hat, how to break Samsung. This is more on Cortex-A TrustZone, and last one is also on Cortex-A. It's interesting attacks on devices. So, and of course, this is just a short list. There's a lot of stuff and a lot of research that you can find in hardwear.io events as well that talk about those attacks. There's a lot of stuff interesting here. So with that, I would like, first of all, to thank you for your time. I think we actually exactly on the time, and I'm open now if anyone have, of course, anyone have any question or need extra information. You can feel free to contact me. I will put my email again right here. Yeah, so you see this is my email here, Oren Hollander, Oren H. Please, okay, and so feel free to even send question after the session, no problem. Andrea mentioned that this is a recorded session, so you can go and hear it back. Very efficient. If you cannot sleep at night, you can hear it again until you get sleep. But I hope I gave you enough information and make things interesting. It's a big topic, and I would like to mention that the hands-on training provides all the security trainings and ARM trainings and also FPGA trainings. So if your company would like to have something deeply with hands-on practice, you can contact us. And I hope to see you in the next sessions as well.
Thank you very much, Oren, for your presentation. I think it was well explained, and I think people take some time to digest it, but we already got a question from Amit. How to debug a TrustZone-based application? Any challenges in debugging? Is there anything called as secure debug?
Oh, very good question. I didn't cover that, but first of all, it's important to understand that the way to generate projects for TrustZone, you actually generate two projects in your SDK. One, the non-secure, and then the secure. And then you link them together at the end. Regarding debug, this is usually depends on the silicon vendor. So ARM provides a way to prevent debug access to the secure world. There's a special lines, physical signals that can prevent access to the secure world. However, it prevents also, let's say, privileged and non-privileged software. So in Cortex-M55, for example, they differentiated, they added a new attribute called PXN, privilege execute never. So you can, for example, provide a technician to access the secure world, but just debug non-privileged library or user space, if you like, and the kernel will be prevented. So usually, in order to prevent debug, there are several ways. One, to prevent debug completely. That means kill the debug, kill the JTAG and trace signals. But this is not good because then the company or the manufacturer cannot debug it as well. So usually what's happened is that the silicon vendor add a special block called the secure JTAG controller, which do secure debug authentication. And then there's some challenge and response to provide some access control, access permission to a specific area. So there's a way, let's say, to debug, and there's a way to prevent debug. But this depends on the CPU configuration and what envelope the silicon vendors put around that. Okay, so it's a big topic. If you would like to see an example, you can go, for example, the device that I mentioned here, the LPC 55S69. I mentioned that because we have our hands-on labs are based on this device. It's a great device. You can find there all the answer for your question. You will see the architecture, how to prevent debug access to the secure world or how to enable it, all the options.
Thank you, Oren, for answering the question. Are there any more questions? Maybe we can take another one. No, I think that's all for today.
Good.
Once again, thank you very much for the presentation, Oren. And it was a pleasure to have you with us today. Guys, please don't forget to fill in the feedback form. It will also pop up after a Zoom meeting is over. And yeah, see you next time. Thank you.
Bye-bye.